Welcome back to Impact Quantum, the podcast where qubits get curious. And entanglement isn't just a relationship status, it's a career path. Today's episode is a real quantum leap, as Frank and Candice sit down with the ever-engaging Alex Khan, author, educator, and quantum computing pioneer who may or may not be on a first-name basis with every photon in College Park, Maryland. Known for his book Quantum Computing, Experimentation with Amazon Braket, Alex joins us to unpack the not-so-light-speed evolution of the quantum ecosystem from Amazon's quantum ambitions to ion traps, optimization, and whether Excel can really prepare you for the multiverse. We talk hype versus hope, entanglement without the emotional baggage, and why quantum computing might just be the new GPU. So brew your favorite beverage, align your qubits, and prepare your mind for a journey into the wonderful world of quantum weirdness. Let's get entangled, shall we?
Hello and welcome back to Impact Quantum. Start that over. Hello and welcome back to Impact Quantum, the podcast where we explore the emerging field and ecosystem of quantum computing and how it's really going to take a village, a quantum village of quantum curious people. And with me is the most quantum curious person I know, Candice Kahuli. How's it going, Candice?
It's going great. I'm really excited about today's conversation. We've been having such great conversations, so I'm just loving what we're doing, and the curiosity is just exploding all over the place. It's really good.
Absolutely. So I'm really excited about having our current guest because when we did the pre-call with him to talk to him, I was like, that guy's name sounds familiar. And then he mentioned that he wrote a book. And here is the book. I told him that I can't get it into focus, but for those of you who didn't see that, it's Quantum Computing Experimentation with Amazon Braket. And our guest today is Alex Khan. Alex Khan also lives in the Old Line State, or the Old Bay State. I forget what the official nickname of Maryland is. We were talking recently about these various quantum hotspots around the world. And one of them is College Park, Maryland, where he used to work. So welcome to the show, Alex.
Yeah, nice to be here.
Awesome. And when I think College Park, most people will think the University of Maryland. I think of IKEA because the large IKEA in the area. And my wife does a lot of IKEA furniture building and things like that. So welcome to the show.
Thank you. Yeah, I'm glad to be here.
Cool. I have to confess I haven't finished the book because, but I did get through quite a bit of it. It's very well written. It discusses kind of the Amazon Braket service, which I haven't followed where Amazon is with that because I tend to be very Microsoft focused, unfortunately.
Okay.
And now I'm at Red Hat. Now I'm very IBM focused too. So tell us what made you want to write the book.
Well, actually, it was Pack Publishing that reached out to me, and they had obviously heard about my different papers or involvement in quantum computing. When Amazon Braket came out, I had, before that, even with D-Wave, I had made some videos about how to get into D-Wave, how to do optimization problems with D-Wave. A lot of the concepts were just very new for me as well, annealing and qubits and optimization. And so I made some videos. Same thing with Amazon Braket. The moment IonQ was added to Amazon Braket, I wanted to get my hands on it, and then I made a video of that, letting people know how to use an ion trap, and I use a simple example in there. So I think Pack Publishing heard about it, and they wanted me to leverage my experience with using different optimization problems with Amazon Braket. So I think I was a natural fit to write it at that time. I mean, right now, I think there's a lot of people that have been used Amazon Braket. Amazon Braket has a very solid team. They have a lot of blogs on there. But in those early days, I think maybe I was the only one of the few people out in the ecosystem that could write that book.
I still think you're a great author. Like, so, don't discount yourself. I would love to see another edition of the book and things like that. Because I know this field changes pretty rapidly, and
Yes.
I think 2025 has been a crazy year in quantum, and we're recording this on April 10th,
Right.
right? It's already been a wild year. And I would say for me, the kind of I'd been sparked my interest in quantum in 2019, and then spark kind of died out. But like this time for me was when Google announced the Willow project and their results from there, and then suddenly, the CES kind of debacle, and then just the recent rapid fire announcements from Amazon, from Microsoft, from all these players, international players. So what's your take on 2025 so far this year?
Yeah, it's overwhelming to some extent. I mean, I I try to keep up with what's happening in the ecosystem and what algorithms are coming out, what new systems or devices are being added to Amazon Braket. So every year, it's just a little harder to keep up with everything. So even last year at the University of Maryland National Quantum Lab, I just saw a lot of work happening inside the university. I mean, they're working on algorithms, they're working on sensors, they've got various superconducting quantum computers over there that they're researching, various use cases. But then they're also doing, using the chips for quantum gravity and for quantum sensing, and they're building the quantum internet. So, I mean, there's just so many areas in just one place. And so when you start multiplying that now, where every country, every university wants to get into this, there's just, new papers, new ideas, unique, creative concepts, new ways of teaching coming out from every area. And, there's more books. So it's very exciting. It's definitely a growing field. The quantum hardware is also growing. There's a lot of new companies that are building quantum hardware. I mean, Amazon also built, have announced their quantum computer. So in that sense, I think it's an amazing field to be in. Every day there's some excitement in some area, new benchmarks. So yeah, it's all I can say is just hard to keep up with it. And I've tried to follow more of the optimization route. That's kind of my area, and it's kind of become my area of expertise, though, as you'll hear, I'm working on all kinds of other things as well.
Interesting.
Yeah, and that's what I find, because there's so much information coming out about every aspect of quantum. It begins, you understand that just when, for someone like me who's curious, but who's been in the tech sphere for over, 10, for a few more years than that, you get involved with it and it's exciting, but then you have to kind of decipher what's real, what's hype, and what means what to whom, right? So
Yes.
you're excited when you get to hear about the oscillate. You're excited when you hear about Majorana. But then when we speak to people who are more on the academic side, they're explaining to us, well, it's a little bit more hype than you might think, because there's error correction issues and scalability issues. And there's a lot of things behind the scenes that, aren't quite there yet, So how do you feel about kind of that divide that there is between, the physicists, the academics, the engineers, and then those who are trying to kind of put this into commercial use, who are trying to find, their quantum algorithm that they're going to use for the next thing that they're going to work on? what is your thought on that?
So, I mean, I think there's definitely a big gap between, where we are and the hype. Sometimes the hype does get way ahead of itself. But the reality is that this is a very interesting and very innovative technology. Like IonQ's founders have been working on this for 30 years. When they were working with atomic clocks, and found a way to actually calculate and do a calculation using a qubit. So it's taken a long time, and there is obviously a lot of development happening. So when I started in 2019, there was only a 5-qubit quantum computer, that I could use with IBM. Now we have 100-qubit quantum computers. It was, I think, 2 years ago when DARPA did a RFP for building one logical qubit. I mean, just one logical qubit. Now we have multiple logical qubits, and the error correction codes are getting better. Before, we thought it would take 1,000 actual physical qubits to make one logical qubit. I think now it's less than 100. So, there's a lot of development, a lot of new ideas. So, and I think it's also progressing, very rapidly, because a lot of companies and a lot of researchers are working together in this. So there's definitely hype, but I think that's because sometimes the communication, the way it reaches the market, and then when people try to simplify it and write it down, and of course, they want to get more eyeballs on the paper. They'll make an announcement, XYZ company had this new revolutionary advancement. It just gets blown out of proportion. But the people that are reading the papers and that are in the field, they see steady incremental progress. So for us, I see all of those, and I try to help out and explain as much as I can to the people that are following me. But I mean, we're seeing, very solid progress on a constant and rapid pace. So I think it's all good. I think, at one point I was also worried about the hype, and then I realized you need a little bit of hype to get people excited and for the general public to pay attention. If there was no hype, nobody would be, even interested. You wouldn't get this information out to the high schools and to the students, and for them to want to even pay attention. So I think it's, as long as somebody is not inflating something too much and blatantly saying something that's not true, I think it's good to have the excitement out there.
There is a fine line between hype and fraud, isn't there?
Well, I mean, if you're a public company and you're saying something incorrect, then obviously that's different.
I also think too that VCs are not gonna. It's a lot easier to raise money once you build the hype around you, right? Like, you have to put a little bit of a ketchup on the burger right now to make it more palatable, because it is a long play. Like, I think it's still a long play. Like, now, is it a 3-year long play, 5-year long play, or, as Jensen Huang kind of said, then walk back, a 20-year long play? I don't think it's that. I think it's not. If you want to make a quick buck, I don't think quantum is really the place for you. If you're an investor, I think it's one of those things where there's going to be a massive long haul investment. I could be wrong, but I always preface
I can't really comment on that. But if you think about, like our goal to want to go to Mars, I mean, that's a lofty goal, and you have to start somewhere, and you have to start putting the pieces together, and it's a complicated project. Now, I think the difference between going to Mars and making a quantum computer is that Mars is still in the same orbit. But, with our computing, classical computing is always getting better. So it's like Mars is getting further and further away as time goes by. So it is more challenging when you compare quantum computing to classical computing. And it would be like when the GPUs came out, and we were playing video games, if you were trying to compare a GPU to an actual computer, classical computer, you would say, well, what's the value of a GPU? But the GPU did one thing really well, and it got a lot of people excited about video games and rendering, light tracing and all of that. So in that one niche market, it started to make an impression. And, it grew with that market. I mean, people didn't care if the games were kind of rudimentary and it wasn't perfect. It's like we funded and we kept paying for better and better GPUs and funded that whole industry of making better games and better software, and the hardware got better. And I think the quantum computers will move like that. I think it becomes challenging when you're trying to compare a quantum computer right now to a classical computer. And I don't think that's really a fair comparison. I know that VCs and different industry leaders will obviously want to have some advantage over classical computers, but I think the important thing is, for now, at least the way I see it, and for most quantum enthusiasts, to just use the quantum computers and learn how to use them, and then I think innovate and come up with new use cases where maybe a quantum computer has a niche market, and the classical computing is not really in that market as much.
So, given the experience that you have with Aligned IT and some of the other ventures, what do you see as the most promising real-world application of quantum computing?
So I'll try to answer that in two ways. I mean, there's obviously a lot of different areas and applications, and it would be like asking, when the first transistor came out, what would be the best application for a transistor? Right? I mean, at that point, you wouldn't be able to imagine what the world would look like with a transistor, right? So I think that's what we're trying to do. We're trying to imagine what this world would look like with quantum computing. And quantum computing, as you see in the book, is dramatically different. It's solving potentially the same problems, but in a very different way. You have to think differently. Even if you don't think about how the calculations are actually happening, and the fact that you're using qubits or, a superconducting qubit or an ion trap, the fact still is you cannot solve the problems the same way as you would writing a normal code. So now, where would there be the most impact? So what I have found is that in my area, since quantum computers have this property of superposition and entanglement, they can basically connect two variables together. So if one variable changes in a certain way, the other one will change with it. So naturally, the quantum computer has the property of correlating variables together. So you can think of all the applications where you have correlated variables. And portfolio optimization is a very simple example where one asset is correlated with another asset, either negatively or positively. If one asset goes up, the other one goes up, or if one asset goes up, the other one goes down. So you could code that in a classical computer, but with a quantum computer, you just have to correlate the two variables, whether it's on D waves annealer or whether it's in a gate quantum computer. You just have to put in the right rotation. So once you do that, those two variables are now correlated, and then you can imagine all kinds of problems that you can solve where you have these two variables connected. And that's where the whole combinatorial optimization with quadratic terms becomes a natural fit for a quantum computer. So, I mean, there's millions of applications like that. And I think, there's a lot of development happening in QA/OA. So that definitely is an area that will continue to grow. There's not a quantum advantage of the QoA algorithm, but it's going to continue to evolve. But that's a natural thing that a quantum computer can do. There's quantum chemistry. Now, that is also kind of an optimization problem. You're looking for the minimum energy of a molecule or of some property. So in that sense, there's a lot of applications there, and so there's another algorithm, VQE, where people are using VQE, which is a quantum algorithm, to solve energy problems. So they have to build a Hamiltonian, and then they embed the Hamiltonian into the qubits, so into the quantum circuit, and the system will naturally, go to the lowest energy value and give you that. So I mean that is very possible. But what I'm also finding is that with the noise, since the qubits are still noisy, and we still have only a few qubits, even 100 are not fully connected. You cannot think in terms of one variable to one qubit. I think, as I have developed my own understanding working with quantum computers, it was easy to take a variable and say, this one bit of information is equivalent to one qubit. And that's a very expensive way to do quantum computing. So, you're using one bit for one qubit. But now we are looking at solving very large data problems. Like I'm working with a team on a genomics problem. If I was to take one base of a genome sequence and embed it on one qubit, I would need 10,000, a million qubits to embed, a 10,000 base sequence. That's not really going to be very useful. So what we have to do is we have to think about how really leveraging quantum computers, where you use the power of 2 to the power n qubits. And so every time you have more qubits, you get a 2 to the power n increase in variables. So these are called amplitudes. So, for example, with 2 qubits, you have 4 variables, or 4 weights, or 4 amplitudes, or 4 probabilities, however you want to call it. But consider them as 4 knobs, or 4 variables that you can work with. Well, by the time you get to 13 qubits,
that's a big number.
Hopefully, it's like 8,000 something.
Right.
So with just 13 qubits, now you have 8,000 knobs or variables that you can work with. So now I can embed an 8,000 long chain of genetic information potentially into that. So this is, but we haven't done a lot of that yet. So we're working on algorithms. We're trying to figure out how do you embed that information into the qubits. How are you going to calculate once the information has been embedded? How do you store that information? So there is a lot of potential, but I think we have to come up with the algorithms. And the hardware will progress and get there, but we don't even know how to use that technology. So I think that is what we have to prepare ourselves for.
Well, in terms of preparing ourselves, I know you also have experience in academia. And so it kind of makes me wonder if what we are currently teaching in universities for quantum computing, if what we're teaching is correct, or if we should be teaching something else now that you're kind of practically in all of it. Is there any kind of perspective that you have on things that could be added to the curriculum or should be more focused upon as we're bringing up, the next generation, they're the alphas, and even Gen Zs, we have an opportunity to teach them, the right things, while they're excited about it. Do you have any thoughts on that?
Yeah, definitely. So I taught quantum computing at Harrisburg University, and then when I came to the Q Lab, UMD Q Lab, I was given a few students, or some of the students were selected that would be doing the extra work of doing a project with me. So I got an opportunity to teach them. I will say that learning quantum computing is a long journey. You have to be really passionate about it. And it's like any discipline, whether it's computer science or biology or chemistry. It takes many years. It's a long journey. I think I I don't think it's useful if you just want to get a quick return on your investment. Take a few videos on YouTube and things that you can get into quantum computing. There are just a lot of things to consider. Like we already talked. You have to know what kind of qubits you're dealing with, what kind of algorithms are out there. You have to decide whether you're going to be doing the coding and writing software algorithms, or you're going to be writing a software stack, or are you going to be working on building the quantum computer? So there you've got various other disciplines from physics and heat transfer. I mean, chemistry probably, material science, optics. So I think the field is really growing and trying to understand itself. I mean, a few years ago, there wasn't even really degrees you could get in quantum information science. But math is the definite basics the further you can go in math, the better you're going to be in quantum computing. I mean, that's pretty much a given. Every day I'm like struggling with how much I can do because of my own math background. So
That makes me feel better because, like, I read these quantum books and, like, it used to be 15 minutes in and I get a headache and I'd have to stop. Now I can get to about 45 minutes. But yes, that's good to know. I'm not alone on that.
yeah, I mean, I struggled with that as well. And then I was working on a density function, and then in chemistry there's the density function theory, and I mean, I don't know this stuff, so I'm not a chemist. Um, but it's a field that really just pushes you if you're excited about it. It's like you want to climb a mountain and you want to get to the top, and there's just all kinds of challenges in your way, and you have to just keep pushing yourself and overcoming one challenge at a time. So I mean, I'll say for the education is definitely improving. There's a lot of people that want to figure out how to teach the next generation quantum computing. I mean, I've tried to do kind of my best in explaining to my book was written more for professionals, architects that are already in the industry. They already know computing, and let's say their boss tells them that go, I've heard about this quantum computer, is this something that's useful for us? So I mean, I wrote it for that audience, for them to be able to quickly browse through the book and really see what is quantum computing, what does it look like, what can it do, what do these devices, what are they capable of, and then they can decide on their journey. But when I was teaching high school students, we had to start at the very basics and, just matrix multiplication and making sure that they understood that part. I've also taught, I had classes where I was teaching just general business majors, and they were not interested in building a quantum algorithm or, they would never build a quantum computer, but they just wanted to know generally what is quantum computing, so that if they're working for a company, let's say they're in the procurement department, and their manager says, we're buying a quantum computer. So how would you begin to evaluate what a quantum computer is? And one company is saying we've got 30 qubits, another one is saying we've got 50 qubits, and one is saying I've got this fidelity, and another one is saying we have an error corrected quantum computer. how would you even know what questions to ask, right, to determine whether you're going to buy the right quantum computer? So that, that was a very different market that just wanted to know the terminology and the basics. They were very excited to take the course, but I mean, they were not very interested in getting down to the math level. So I think it depends on the audience. There's a lot of room for everyone to join into the quantum ecosystem, whether you're doing marketing, whether you're in procurement, whether you're, in conferences, building, setting up conferences, doing podcasts, right? There's a lot of opportunity to bring existing skills or whatever your passion is. You're in computer science or chemistry or gaming. I mean, I built a VR application. We can talk about that later. But
very cool.
So, I think there's a lot of opportunity, a lot of different ways to think about quantum computing, and it really depends on the person. Where do they want to go in quantum computing, and what mechanism they can use to go from point A to point B. And really, I think everyone's journey is going to be a little different. I mean, I've not seen two people that have the same journey in quantum computing.
I think what you touch on is really good. And I'm glad you're here because you're one of the few people, probably the first guest we really had, that has an equal footing in academia as well as industry. People with 50-50 ratios there are pretty rare anyway. But, when you think back to the early days of classical computing, right, it was largely the electrical engineer types and people soldering wires together. But if you look at as it developed over time, we have graphic designers and we have like the whole everything from soup to nuts in terms of what the skill sets are needed. So I'm very glad to hear you validate kind of our thesis for the show is like you need quantum curious people.
I'm also like the first time. I really appreciate him talking about the marketing, the sales, the business minded.
Like everyone forgets about procurement.
Was beautiful because it really shows what an all-encompassing field that it can be for people with a variety of disciplines. And they are needed. So that was great. Thank you. I love that, Alex. That was fabulous.
I also feel a lot better about my oldest's choice to take AP Physics next year over AP Computer Science. So
well, I mean, you're going to have to program both. I mean, no matter what field we're in now, you have to know a little bit of programming, or at least know how to use ChatGPT to create a program.
Exactly. Yeah. Vibe coding. Yes.
Right.
Yes.
Exactly. Exactly.
I predict a lot of money will be made by consultants fixing vibe coding and updating and patching vibe coding applications, but that's just the cynical side of me. So what do you think is really kind of where do we go from here? Like, and in terms of like, if quantum is definitely, I think it's out of the lab, but I think it's also in that weird adolescent phase of it's still heavy on the research. I think data science followed a very similar aspect to this, right? Most of what we call AI is really data science, and most of what we call data science was really statistical and mathematics and kind of PhD level statisticians and mathematics. And I think there was a lot of gatekeeping in the field early on, but it kind of exploded. And I think that where do you think we go from in quantum? Do you think that where do we go from here in terms of building out an ecosystem? Like what do you think needs to happen next versus what you think will actually happen next?
Well, I mean, to build the ecosystem, I think, we just need more marketing and depending on when you want to pick up somebody, right? If you want to pick them up in 6th grade or 9th grade, I think there are different ways of introducing quantum. Generally, it's quantum mechanics, right? Quantum mechanics was a class that, you didn't normally take till you were in upper level classes in undergraduate. So I did take quantum mechanics classes. So, and it was probably the most complicated, confusing class that I took. It was, so I'm a mechanical engineering major, so it wasn't something I could put my hands around. So trying to get a new generation of people to really understand quantum means you have to start introducing these concepts, quantum mechanics or superposition or entanglement or quadratic or um, combinatorial optimization in the math early. So we need students who are really see that, they see an opportunity and they're told these are the classes you can take and it will get you there. They'll get you on the journey. So that's one way. I have also seen a lot of books where different authors are presenting quantum in different ways. There's Bob Koch's book, Quantum in Pictures. There's Konstantin's book on programming quantum computers, and it just works on probability. So it just basically says a quantum computer is like a probability controller. I'm going to simplify it. You just maintain the probabilities of those variables, right? I said 2 to the power n variables. So how do you change those probabilities? There's, certain options. And actually, that's for me even that book is great because you really begin to see if you're going to build an algorithm, you have to think about this is what you have. You have this device that changes probabilities. Now, how do you get to where you want to get to by doing that? Right? If you're building a sandcastle and you were given sand, that's what you have, right? So now you've got water, a cup, and you're trying to build a sandcastle, right? So that's what you're working with. So I think that is, you have to play with that. You have to kind of get intuitive with this tool. So, so to build, so you're saying, where are we going to go from here? I think we need better, teaching tools. We need people motivated to get into this field early. Every layer of the stack, I think, has its own challenges. So whether it's on the hardware level, and there's multiple kinds of qubits, photonics or ion traps or superconducting or quantum dots or cat qubits, neutral atom. Each one is different. Each one you have to program differently. The algorithms are different. What you can do with it is different. So I don't know if in the future we're going to have these specialists that are like neutral atom specialists and
photonic specialists, right?
Right.
So the software layer, the coding layer doesn't abstract away a lot of that, or not enough.
Well, if you think about it, each of these quantum computers uses a certain physical property. So neutral atoms are using a property where the Rydberg atom grows, the outer layer shell grows, and it uses there's a quantum property where 2 qubits can't have a different state. No, actually, 2 qubits can't have the same state. So if one qubit is 1, the other one becomes a 0. So it forces one of them to change its state if you want to have a state on one of them. I mean, that is the physical property that they're using on the Rydberg atom or neutral atom systems. So like QEra, atom computing, inflection, Pascal, right? Those companies are using this one specific property. Now, with that property, you can have thousands of qubits in a lattice, and you can create a 2D structure. You can position the qubits wherever you want to position them. And then once you build this, grow this Rydberg radius, you start impacting qubits with each other. And so that system naturally solves the maximum independent set problem. It prevents, depending on how far you grow that Rydberg radius, you kind of bring different qubits into that one state where you can't have 2 qubits with the same value. So with that, the system naturally does maximum independent set. And with that, they are looking at what can we do with it. So, they're trying to solve all kinds of different chemistry problems or optimization problems. But the system fundamentally is built like that. And so I think there's a lot of nuances and challenges and opportunities on how that system will be developed, how those systems will evolve, and what you can do with them. Now, what I just mentioned is the adiabatic or the it's a different regime where the Rydberg radiuses grow when you shine the microwave or the laser on them. But you can also then build finer lasers that touch or affect each atom independently. And now you can start treating each atom as a qubit and start doing some digital gate operations on them. So now you've got kind of this adiabatic or annealing type of system, along with the Rydberg system or the maximum independence set system. Plus, you can do some gate operations. So I don't know what you can do with that, right? I mean, this is just like new technology that's coming out, and there's a lot of researchers writing papers where they're learning from these systems and trying to use them for different applications. So it is really a very nuanced field. You cannot just put it all in one brush and say all quantum computers are equal.
Right.
Like the photonic systems, they have a very different way of functioning. You have to send thousands of qubits through photons. You have to entangle them first and then send them into a circuit. And the algorithm there is called a measurement-based algorithm, kind of like quantum teleportation. So,
okay, that makes a lot of sense now.
So, I mean, that's a different way of even writing or thinking about an algorithm. It's almost like you've already got the entanglement there, and now you're writing an algorithm where you are measuring one qubit and expecting the other qubit to do what you want with this one qubit. Since they're entangled, if you manipulate one qubit, the other one is going to change as well.
Right.
And you're constantly manipulating one and expecting the other to do something different. So it's, again, that's a very different way of even thinking. So the question is, all right, well, what can we do with that? How is that going to be useful in the future? And that's what I'm talking about, that each of these systems have a lot of nuances, and you can spend, I think, your whole career working in one modality and really understand it. And it just depends on where do you want to actually be in that software stack? You want to be at the pulse level where you're controlling the qubits and sending the microwaves or the laser pulses, the Rabi rotations. Are you at the control system level? Are you at the algorithm level? Are you at the use case level? So, and none of this has been figured out. So, everything.
I think it's very analogous to kind of in software engineering, right? Where people they build up their career in, say, the financial services industry, right? And they're, when labor markets get really tight, they're like, well, no, we want someone with private equity experience, or we want someone with mortgage, like they were, but I think that I think it's probably gonna shake out something like that. That'd be my guess.
Yeah, no doubt. I mean, it's like if you get an MBA, and you can go a million places with an MBA. You can go into consulting, or you can go into finance or management or anything. So, and one example I was thinking of when you were asking me these questions was, like when Excel, when Excel, or what was it, Note 123 or something like
Lotus
that
Notes.
came out.
Yeah.
Lotus Notes. I mean, there were some people who just got it, right? They got the cell structure and how you can calculate from one cell into another cell, and you can put a function. And there were other people who just never got it.
No, that makes a lot of sense. And I know Candace is itching to ask a question, but I just want to add one last thought. When somebody had told me that by and large the software will abstract a lot of the underlying hardware thing, it sounded a little too good to be true. So it sounds like it might be a little too good to be true. Is basically what you're saying.
You can. I think, for example, if somebody was trying to build a traveling salesman problem, and all you wanted was the client to put in their cities or their locations and the distances and all of that, then yes, you could potentially have many layers going into converting that problem into something that eventually is solved on that quantum computer.
Right.
But I think the point I'm trying to make is that maybe that's not the right problem for a Rydberg atom system, or maybe that is the right problem for a Rydberg atom system, but it's not the right problem for a photonic system. Or, so we don't know which problem these different quantum computers will solve more efficiently. And I think it would be like, we have GPUs.
Mhm.
So GPUs do matrix multiplication, and they became a natural fit for a lot of the matrix multiplication you need to do when you are creating a 3D environment, and you do a rotation, or you look from from one angle to another angle. Just that shift in perspective requires every element to be recalculated, right? And it's the same calculation over and over again.
Right.
So the GPU was a natural fit for that particular matrix multiplication type of a problem. Now, if you were to say, well, can we use it for all kinds of other things? Well, you probably could, but is it going to be the most efficient tool to solve those problems? So I think it is. I mean, obviously, every company could say that my quantum computer can solve every problem, but I don't think they're going to say that. And I think what eventually we're all going to realize is that annealing quantum computers can solve optimization problems better. Gate quantum computers are going to solve certain kinds of problems. If you have like an ion trap where every qubit is connected to every other qubit, you're going to be able to solve more matrix problems where you have more entanglement between the variables. But if you have a superconducting qubit where one qubit is connected to 2, 3, or 4 other qubits, that's not going to scale very well. So you're going to have to solve nearest neighbor type of problems more often on those systems. And there was a company, Bleximo, who was actually trying to build quantum computers that were customized to the problem you're solving. So, I mean, I think once we figure out what these devices are, what they can do, how can we control them, we might be creating new kinds of quantum computers to solve specific kinds of real-world problems. So, yeah, so it's still, I think, up in the air.
Interesting.
We know there's a lot of things that you've talked about, all of which are incredibly fascinating to this curious self. So I'm going to ask you a question just kind of to understand something. We talked about the different kinds of qubits. We've talked about, how those different types of qubits will be good for different purposes of real world problems. I'm curious to know, number one, is entanglement the same by definition for each type of qubit that you're dealing with? And as a follow-up to that, I would love for you to give us a 60-second definition of entanglement.
So, entanglement is a quantum mechanics property where when you entangle two separate things, whether it's photons or electrons, you bring them into one state. So from a quantum mechanics perspective, they're not two things anymore. They're basically one thing with one state. And so when you change that state, or when you affect that on one side, the other side changes naturally. So, the simple example is that you've got two photons, one is up and the other one let's say you entangle those two photons with where if one is up, the other one is up as well. So that is, let's say that's correlating those two photons, positively. You can also correlate them in the opposite direction, where one, if you detect that one is up, the other one will always be down. So those two photons have become one state. And so the property of one and the other is not different. They're not separate things, they're one thing. And so in nature, you can take those two photons apart, light years apart, but that state remains entangled so that if you affect one, you're still affecting the other, even though there's a distance where light cannot travel from point A to point B and give it that information that you have, affected one photon. And this is the idea behind quantum teleportation and quantum communication. But photon is, the light can move at the speed of light, and you can have distances. That same property we're doing on a chip. So when we are entangling two qubits together on a chip, you're still making them into one state. And so with that, you're able to, like I said, correlate variables, correlate two things together. And it's just a property of nature. And so you're asking, is that one property for all qubits? Yes, it is. It's, whether,
Okay.
It's, and once the actual quantum mechanics property of entanglement is the same. However, not all quantum computers are using just entanglement. Like the Rydberg radius is a slightly different quantum mechanics property when you are dealing with the Rydberg radius encompassing two atoms. Or the electron shell of one is going over the electron shell of the other, and they become kind of an entangled state. So there are different quantum properties that are being utilized in these different systems.
Interesting. This has been a fascinating conversation. I really enjoyed it, and I don't want to be respectful of everyone's time, but we'd love to have you on the show again and kind of deep dive. And if I do bump into you next week, I'll bring my book along so you could sign it if you don't mind.
All right.
And
no, definitely.
Awesome. And where can folks find out more about you?
But LinkedIn is the best place.
Okay.
So if they do a search for me, Alex Khan, on LinkedIn, it's Alex Khan MBA.
Okay.
And my company, Aligned IT, so they can go to www.alignedit.com. I've got a lot of information there. I've got some videos and different papers that I've written are all kind of listed over there.
Excellent.
So yeah, those are two places.
Excellent.
Fantastic.
And I'll let our AI finish the show.
And that, dear quantum curious listeners, brings us to the end of another episode of Impact Quantum, where we explore the world of quantum computing one superposed step at a time. Massive thanks to Alex Khan for joining us and giving us a front row seat to the quantum evolution. From optimization to entanglement, from academic ivory towers to Amazon Braket. He's given us a lot to think about. And probably a few sleepless nights wondering if our spreadsheets are secretly quantum algorithms in disguise. If you enjoyed this episode, be sure to subscribe, leave a review. Or better yet, recommend us to someone who still thinks quantum is just a fancy way of saying really small. And remember, in the quantum world, uncertainty is just another way of saying infinite possibilities. Until next time, keep your states coherent and your curiosity entangled. Cheerio.